Alrighty, everybody, welcome. This is going to be a quick video today, not too quick. I want to share a couple articles that I've found and prepared, and they've been out for just a little over a week or two now, and just thought that you might be able to adjust my camera a little bit here, be able to get some knowledge out of them, and I thought they were pretty cool, and so I just want to take the time to share them with you. And the first one is called, it comes from the article titled Hubble on the Hunt, a spectroscopic search for BetelBuddy. It's about astronomers who are trying to confirm the existence and identity of the companion star to Betelgeuse, the great star Betelgeuse in the shoulder of Orion, up there, nice, bright and red, been in the news over the last several years. Great dimming happened a couple years ago, and anyway, the mystery with Betelgeuse is for quite some time now, astronomers have noticed that Betelgeuse goes through these periods of dimming and lighting up again, getting brighter, getting dimmer, getting brighter, getting dimmer. And it's led many to believe that the star Betelgeuse isn't alone, that it has a companion, probably an unseen companion that's much smaller, that impacts Betelgeuse and helps it to go through these dimming and brighter periods. They've nicknamed it BetelBuddy. This article talks about a research team that used a Hubble Space Telescope not to take images, but to use it to try to find this hidden companion through a process called spectroscopy. I'm not saying that right. Spectroscopy, which is the science of using light coming from the star to analyze it and to look for specific fingerprints of ultraviolet light that would only come from a young separate star, the companion star, BetelBuddy, and that would be slightly shifted because of the orbital motion around the massive Betelgeuse of the star. Basically, the conclusion from the article is that the team ultimately did not find statistically significant signal of the companion star. However, the non-detection is important, and it's very useful because it helps us to know that BetelBuddy has to be smaller than we previously thought. Previously, they thought it was about twice the mass of the sun, maybe a little bit more. We happen to know now it's probably, the new data has ruled out that is twice the mass of the sun. It suggests a companion star about 1.1 times the mass of our sun, or maybe slightly less. We happen to know that in December of this year, just recently, that in December of 2024, so a year ago, using the Gemini North Telescope and the Pokey instrument, it was BetelBuddy was officially imaged and found. They named it Sawahari, or Orionis B, or Betelgeuse B. It's estimated at that time to be a smaller, fainter star. They said at that time likely 1 to 2 times. This research study helps us to narrow that down to about 1.1 times the mass of the sun. Maybe a little bit more, maybe a little bit less. We know the companion orbits Betelgeuse in a very tight path. It's not a wide open, it's very tight around Betelgeuse. Only about 4 astronomical units. An astronomical unit is the measure of the distance from the Earth to the Sun, so it's 4 times that distance, which is about 93 million miles. So roughly about 38 million miles. 36, somewhere in there, 36, 37 million miles. So it puts it well within Betelgeuse's outer extended atmosphere itself. The companion star is believed to be the cause of Betelgeuse's long 6-year brightness cycle that it goes through, of brightening and dimming. As the companion orbits, its gravity snowplows or clears out some of the dense dust that's put out by Betelgeuse that it's constantly shedding, changing how much of the supergiant light actually reaches us. However, this binary is not going to probably be around when Betelgeuse goes supernova. Because it's in such a tight, close orbit, the smaller companion star is experiencing strong tidal forces from massive Betelgeuse. Scientists and astronomers predict that the gravitational drag will cause the companion star to eventually spin inward until it is engulfed by Betelgeuse, probably within the next 10,000 years, which sounds like a long time, but in cosmic terms, it's just a real quick blink of the eye. So, if you get a chance, I've linked it in the comments I've put on the post. You can go and look at that study and study it for yourself. That's basically the first one. Awesome to know about BetelBuddy. So next time you're looking at Rigel naked eye, just know that there's a companion there, and it's pretty cool. The next article, basically, I got part of it, got a link to the article off something that I'll share, but it's basically called "The Sun Has Left Home in a Hurry," or as I call it, "The Sun's a Loner. It got out of home in a hurry." The sun's kind of an independent being. So not an independent being, but independent star. The link is in the comments that I post. It's about a new study that uses objects at the very edge of our solar system to figure out how long the star stayed in its birth cluster of stars. So when stars form, they form out of a nebulous cloud, and as that cloud condenses and begins to contract, puts pressure there until it finally ignites into a star. Usually the cloud will ignite a lot of stars. Those stars are gravitationally bound close together at first. We call that an open cluster. Okay? Stars from those clusters will eventually fade off onto their own. Some will go quick, some will stick around and kind of like to be by each other for a little bit of time. Eventually they disperse out. We know the sun wasn't born alone. Like I said, most stars, our sun was born inside a crowded star cluster, a dense neighborhood of dozens of hundreds of other young newly formed stars. And like I said, over time those stars are going to drift apart. But the early close encounters with gravity of the sun's siblings could have seriously messed up the early orbits of planets and other objects orbiting the sun. So basically, the longer the sun had stayed in the neighborhood with those other stars, the planets in our solar system could have really been affected there. Astronomers realized that the scars of those early encounters might still exist far away from the Kuiper Belt, in the distance of the icy region beyond Neptune. That's what we call the Kuiper Belt out there. This new study focused on a small rare group of objects called distant sednoids, which have very stable, predictable orbits that are almost flat relative to the rest of the solar system. The conclusion is, by running computer simulations of different close star flybys, the researchers found that if the sun had stayed in its crowded birth cluster for too long, the gravities of those other stars would have pulled the sednoids into a more chaotic, tilted orbits. They would have left the plane of the ecliptic that the planets are on, and they would have pulled up into a more chaotic, tilted orbit around the sun. The fact that the sednoids' orbits are still relatively neat and tidy today suggests the sun must have left its birth cluster early. It scattered, got out of there, within an estimated 50 million years. Sounds like a long time. Cosmic terms, not too long. Okay? This is the strongest evidence yet for how fast our solar system escaped its original dangerous neighborhood. Probably had a lot to do with the formation of our solar system and the fact that the Earth could eventually support life. You may ask, what are sednoids? Sednoids are a rare class of trans-Neptunian objects. We'll just call it TNOs, meaning they orbit the sun at a greater average distance than the planet Neptune. They are named after the first one discovered, the dwarf planet Sedna. The orbits are incredibly large, reaching out hundreds of times the distance from the Earth to the sun, known as that astronomical unit. They're highly detached. They have a distant perihelion, their closest point to the sun, usually staying farther than 50 astronomical units away. That means their orbits are so far out that the gravity of Neptune and the other giant planets really doesn't impact them significantly, if at all. They're highly elliptical. They have highly stretched out eccentric orbits. Sedna, for example, takes about 11,400 years to complete just one orbit around the sun. Why they matter? The extreme orbits of the sednoids make them valuable fossils for understanding the early chaotic history of the solar system itself. The orbits of sednoids are so tidy they suggest the sun must have left its crowded birth star cluster quickly. Otherwise, the close flybys of other stars coming by our star, our sun, would have thrown the sednoids into more tilted orbits, not the nice elliptical orbits they're in around the sun. The orbits are the first few sednoids discovered appeared to be clustered in a similar direction. The clustering is what led astronomers to propose the existence of a massive, as yet undiscovered world, often called Planet 9, whose gravity could be corralling those distant objects. There are new discoveries that challenge that idea. The recent discovery of new sednoids like 2023 KQ-14, nicknamed Ammonite, whose orbit does not align with the others, has complicated the Planet 9 hypothesis and suggests that there's other explanations, like an ancient stellar flyby of another star or a rogue planet that came and was later ejected out, might be responsible for their strange past. Because they are so stable and detached from the known planets, sednoids offer a unique look at the gravitational forces that shaped the outer solar system billions of years ago. So basically, those two articles, the last one just shows that and I'll be sharing more about open star clusters in the future, as they disperse out, our sun got out really quick, 50 million years, sounds like a long time, but not really in stellar terms. And because of that, the orbits of the planets around our sun maintain basically kind of the inner planet, outer planet system that we have today. If not, the other stars that were coming by and flying by could have really impacted where our solar system ended up evolving to. And I think as a result, it provided the opportunity for the Earth to form and to be able to not be impacted by a gas giant or other things. Also, if you look at it, it allowed Jupiter to be in the outer part of the solar system, and it acts as a kind of a magnet to take away a lot of the asteroids and other items that could eventually impact the Earth, allowing the Earth to develop and continue. Anyway, those are my two articles for this week. I just thought I wanted to share and give you a synopsis of them. They're in the links in the information on the post. Take a look at them if you want, and have a great day. Keep looking up.